We're still on linear correlation, but now we're going to focus on a term called linear regression. Linear regression is linear correlation. They just call it regression because it's straight lines, and straight lines get that name. We're going to go through a lot of theory today, and then with a bit of luck, we'll start some of the questions on the homework. And then after that, on Monday, we'll finish this off, and that will be us finished for the quarter. And so Tuesday and Wednesday, we're going to devote that to revision for your final. So that's kind of my goal. And your final is on Thursday. Okay, who shall I pick? Liana, what time on Thursday does the final exam begin?
10.
And it finishes at, yeah,
1. I think it's 1.
10 to 1, right? And it's going to have the same format as the midterm. The final will be cumulative. That means everything from week 1 until, whatever we do next week, we just finish this off. So bear that in mind. Don't just study the last 4 weeks and think that's all's going to be in it, and you'll be unpleasantly surprised.
Okay.
So let's start with what are regression lines? Well, you collect your data and you make a scatter plot. Then you'll have an X and a Y axis. Let's give them names. Let's have X, the area of a house, and Y being its value. In other words, what you could get if you sold it. And if you plot area of a house against what it sells for, it wouldn't surprise you, I think, that it would at least be positive. And it depends on the area. It's probably going to be pretty linear, right? That seems reasonable. Big house costs you more, little house costs you less, right? And we would like to take some data, the scatter plot, and we would like to be able to draw a straight line that represents that data. Great, that would be a useful thing to be able to do. Now, if I gave Aidan this data and I gave Liana and then I gave Brandon the same data and you all plotted it on square paper and you got your ruler and you drew a line, would you agree it'd be a freak of nature if all 3 of you drew exactly the same line? Yeah, mine's a little bit steeper, yours a little bit shallower, mine's a little bit down, yours is a little bit up. So you could draw lots of lines. What you might not know is that there's one line that's a better fit to the data than any of the others. And it's a mathematical unique line, right? There's a process for calculating it. But the way that they do it is essentially, this is a kind of simplified version of it. You find the distance, the vertical distance of every point to the line that you're talking about, right? So all these guys here, right? You see all these little green lines. Now, can you imagine that as you adjust that line in location and steepness, won't these distances change for each line? But can you imagine there might be a line where these distances are at a minimum? In other words, the smallest error you could get, right? That is the line. That's the unique line, and it's called the regression line. And here's our first problem. It is called the regression line. In many cases, it's also called the least squares line. It's also called the line of best fit. It's the same line, it just has different names. So if you go watching a video, you might think, what's this regression line they're talking about? Or what's this line of best fit? It seems that this textbook likes that name, which in my list is the ugliest name of the lot. I like this name. Doesn't that give you a better idea what the line is? It's the line of best fit. I think that's a great name for it, but that's not the one they're using. So you're going to have questions and they'll talk about the least square line. They're talking about this one, right? The unique line that's best through the data. That's my least favorite. I like this one the best. I would say that's a close second, and I hate this one, but that's what it's going to be called. It's going to be called the least squares line. You're probably going to hear me call it the regression line a lot because that's easy to say as well. Now, a little bit of algebra to do with any straight line, not just this line. Where's my pens? There we go. So I'll do an X and I'll do a Y. I won't do area house. I'll just call them X and Y for a minute. Imagine a line and it was 2x plus 10. You remember doing straight lines? That's what straight line equation looks like. This number here, it's called the coefficient of x. It's the slope of the line. You remember doing lines and 5x would have a slope of 5 and 2x would have a slope of 2 and minus 3x would be pointing down the way with a slope of -3. Just out of curiosity, can anybody remember what you call the plus 10, the number? It has a name.
No.
Okay, it's called the y-intercept. So basically, that guy there would be 10. See if it was 2x plus 7, would it be down here? If it was 2x minus 7, it'd be over here. If it was 2x plus 100, it'd be somewhere up there. It's called the y-intercept. So if you see a mention, what's the slope of the regression line? You're going to say 2. If they say, what's the y-intercept of the regression line? Aren't you going to say 10, right? Just so that you get familiar with the language, right? We're good? So, any questions so far? Yeah. Let's return, well, I'll do a better version of that since I've drawn so many lines. Let's suppose that I collect data on houses in a certain area in Bremerton. And I do the area of the house and I do the value. It's not uncommon that the data is linear. So pretend that's our data again. And I'll do a green line this time. There's my regression line. There. And I'm now going to tell you the equation of this regression line. And it might be some ridiculously big value, like 210x plus 20,000. Right. Now, y and x have different meanings. X is the area of the house, y is its value in dollars. X is sometimes called the explanatory variable. And anybody know what the fancy name for the y-axis is? Last chance, anyone remember? Starts with an R. Okay. It's called the response variable. Now, if you have data where you're measuring the area of a house and how much it sold for, the regression line, the equation of it, won't quite be written like that. They'll put a little funny hat symbol above it. And so when you write the equation of a regression line, if you want to use x's and y's, it would be written like this. And you read that guy not as the Y value, you read it as the predicted Y value. So the predicted Y value, in this case, the predicted value of the house for any given square footage. So somebody went and said, yeah, you know, I've got a house and it's 2,000 square feet. How much do you think I could sell for my house? Well, if you go up there and you get to there and you read off, that number there on the y-axis is the predicted value that you sell your house for. And the reason why it's a predicted value, don't some houses that have the same square footage sell for more or less than other houses with the same square footage? And maybe they're better decor, right? Maybe they're a little bit better kept. Maybe they've got a better view, right? There's other reasons for the price of a house that's not connected to the size of it. So this would only be a predicted. So if you were a real estate agent, you might use this model and say, yeah, based on the size of your house, I would sell it. I would probably be able to sell it for round about, you know, whatever it is, 250,000, right? Whatever the number might be. So we talk about the predicted Y value. So let's try that. Suppose someone has a 2,000 square foot house, and I'd like to know, a lot of twos in this, how much a predicted value, how much it would sell for. So it would be 210 times 2,000 square feet plus 20,000. And the answer would be that you would predict that this house would sell for about 440,000. That doesn't mean you're guaranteed to get that price. Could your house get a little bit more if you're lucky, and it could sell for a little bit less? You agree? That would be reasonable to expect in any model. So we have a thing called the residual. The residual is essentially the error. So let's suppose this person actually sold their house, right? Now, the error is the real value that they sold it for. Take away the predicted value, right? So it's going to be the real value, take away what we predicted it would sell for. So let's suppose the real value you sold it for. Let's suppose you sold it for 443,000. Then in that case, the residual would be what, $3,000? And since that's positive, wouldn't that mean you sold it for 3,000 more than the predicted value, right? So we have a model here that will allow us to predict what a particular square footage of house might sell for, right? And it's only predicted, it's no guarantee. In fact, in real life, we'd be very surprised if it was a perfect fit. But wouldn't we also expect it to be pretty close to the real answer, right? Pretty close. Now, let me look at this formula again and see if we can take the slope and get some meaning out of it in the context of this question. Now, when you talk about a normal slope, they would say something like this. For every, how would they phrase it? For every increase in x by 1, or every increase of 1 in x, won't the y value increase by 210? That's essentially what a slope means, right? If x gets 1 bigger, the y will go up by 200, right? That's the slope. In the context of this situation, for every, let's say, extra 1 square foot of house value will increase by, in this case, the slope, $210. That's actually a number that you will see if you've ever gone looking for houses. Isn't that the price per square foot, essentially?
In the
Now,
city.
right? So, Brandon, if you were going to get a house in Seattle, God forbid you were stupid enough to live there, but let's suppose you wanted to live in Seattle, couldn't you be paying 400, 450, whatever it is per square foot? Because that
Oh, yeah.
houses over
For-
there
for right around
scarily. Sorry, you were saying, Brandon?
For right around the center of Seattle, yeah, they get pretty
Yeah.
crazy.
Right. So what you're going to, isn't that a very nice number that gives you just a general idea of expense of an area, right? And if you go to some really run-down part of Bremerton or someplace, you might get it for like $105 a square foot, right? Different prices for different areas. I bet if you got a house that had a great view of the sea, wouldn't the square footage in that house be a lot bigger than somebody, 2 mile away in the middle of the land with no great view? So we very often use that single number as an indication of, in general, how expensive an area is. So in this case, I know 210 is probably somewhere in the middle.
So would the most accurate way for something like that be to have the minimum per square foot in that designated area, and then have templates for each possible variables, like if it's waterfront, add another $20,000.
You could certainly do that. I mean, people will say things to you like, I'll make this up, not in this area, but let's suppose you're going to get a house in a warm area. They might say, having a swimming pool is plus 10,000. Having a double garage will get you an extra 5,000, right? And having a bigger square footage of land might get you another 30,000. So that would be like your basic, and then you could add on all sorts of, like you were saying, you could put estimates on things like swimming pools and extra garages. And as long as you've got enough data, you can actually do that. Companies like Zillow, who basically collect data on the prices of almost every house, including ones that have not been sold actually, in a while at least, and they collect it. And how you would do, let's say, swimming pools. In one area, you've got to keep it close to each other, right? But in an area, couldn't you maybe find, say, 50 houses that are about the same size, and some had swimming pools and some didn't? And if the houses that had swimming pools sold for about 10,000 more than the ones that didn't, do you see how they could come up with a number? A swimming pool is probably going to add 10,000 to your house. That wouldn't be a good reason to build a swimming pool, because it probably cost you 15,000, 20,000 to build one, only to add 10,000 to the price of your house. So a lot of people forget that improvements to houses don't actually necessarily increase the value of the house by the amount it costs you to build the thing, right? So you might say, well, I'll get an extra garage built. That'll get the value of my house going up. It will, but won't you probably spend more money getting the extra garage than the increase in the value? So you got to be, judicious in improvements. Side issue.
Cost analysis on it before you improve it.
Yeah, you got to look at it from that perspective. Almost every improvement, you'll be lucky if you get 80 or 90% back on the value of a house. So most improvements you should only do because you're wanting to live in the house and you like a swimming pool and you like a kitchen. But the ones that do the best, right, the ones that increase your value by the most, are bathrooms and kitchens. And if it doesn't increase the value by much, because it's probably only going to get 80% return, what it will improve is the number of people who want to buy your house, which is very important as well, isn't it? A nice kitchen that's just been renovated is probably going to sell quicker than a house that's got a 10-year-old kitchen, right? It's just common sense. We're drifting, but that's good stuff. Learning stuff is always good. Y-intercept, what on earth could that represent? Well, technically speaking, isn't the y-intercept the value of the land, the value of the property when the land is 0? Oh, in this case, isn't the y-intercept just the property at the price of a plot of land? So now I'm looking at my model. That's probably not a very accurate model, but evidently in this place, land is cheap, right? You want a plot of land, it's just going to cost you 20,000, right? And then you have to build a house and put in the plumbing and do power and sewage and, you know, all adds up. But y-intercept is the price of the house when you have 0 for x. So slope and y-intercept, put that one in, or I forget, price of the land. Don't they tell you quite a lot about the thing that you're measuring? That is our first one. Let's do another where we look at meaning of slope and all this other fun stuff. So let's suppose that I collect data and we'll have one that's negative this time, and we'll have it so it's pretty good in linear. Look something like that. And what will I have? The number of cigarettes you smoke per week. And right, so I should have put that up there. Doctors collect all sorts of information about the patients, not just the ones that they have, but the ones that have passed on, right? And you know, your doctor, if you're a smoker, not that I am, but if you were a smoker, I wouldn't be surprised if the doctor says, how many do you smoke a week? Right? And they'll keep track of that. And you know, everyone dies eventually. And so you can imagine they could collect it where they don't smoke at all. They smoke, I don't know what, 5 cigarettes, 10 cigarettes, 15 cigarettes, you know, 20 cigarettes, and so on. Can you imagine they could collect that data? That would be an observational study, wouldn't it? Because you don't make people smoke, you just observe what they did, and you know, this indicates the age that the person died. So let's suppose that this person up here died at 90, and this last one, let's say that was 60, just for argument's sake, right? So we've collected this data. Would you agree it's negative? Okay. If I put in my regression line, put a couple more dots to kind of make it more accurate looking, that would be our line of best fit, right? That would be our least square line and all the other names they give to it. That's the guy. Let's suppose then that I haven't told you how you get that line. The good news is that Salt does it for you, so you don't need to worry about how to calculate it. But let's suppose it was y hat, the predicted age that you would live to, would be 95, take away 6 times x. And that's what it looks like kind of algebraically. You could do it like this. Your predicted age that you live to is 95 take away 6 times the number of cigarettes. If you write it that way, doesn't the formula look a little bit more obvious what it's doing, right? This guy is that guy, right? Now, I can use it to predict the age of a particular guy. So if I was a doctor and the guy came in and I said to you, okay, I see you're a smoker. And what do you normally smoke in a week? And that person says, I smoke 10 cigarettes a week. Then the predicted age of that person, would be 6 times 10. Ooh, okay. Can I change that to 0.6? Otherwise, the person will be dead before we know it. And so what you got, 95, take away 6. You're going to say, hey, you're probably going to live to 89. Someone else comes in and you ask them, how many cigarettes do you smoke a week? And they say, I smoke 50 cigarettes. Can you see that the more cigarettes you smoke, you're probably not going to live as long as people who don't smoke as many? Would that seem reasonable? That's what you would expect to see, because cigarette smoke is bad for you. Now, we have quite a lot of data on all sorts of things, including smoking, because it's such a it's such a well-known danger to your life expectancy, right? There are lots of good data on it, but you can get data on how many units of alcohol you drink per week. And because, where was I going with that? Yeah. The data on that's a little bit weird. Have you ever heard people saying that the Mediterranean lifestyle is very good if you want to live long? You ever heard that? Now, when they look into what do Mediterranean people do that's so good? Well, they do lots of things. For starters, don't they live in a place where there's nice weather a lot of the time, especially the ones by the coast? So that's a good thing, because most people are happier, and mindset has a lot to do with living long, right? They also eat quite differently in a lot of ways, right? They eat a different amount of carbs, stroke protein. And the third thing that they tend to push is, don't a lot of them drink wine? And what we've discovered is that alcohol is not like cigarettes. You know, cigarettes are just bad for you. If you take 20, it's worse, excuse me, than if you take 10, right? More cigarettes, bad. Alcoholic beverages are a little bit different. 1 glass of wine a day is actually not that bad for you. 10, you're an alcoholic, right? That's definitely bad for you. So the data for that Mediterranean is a little bit weirder. It's not quite a straight line. It has a little up and then it becomes a straight line. Because people who actually drink 1 glass of wine tend to live longer than those who don't drink any. So go figure that one out, right? So that would be our data. Now I'm going to do something stupid. When you use this model to predict how long a 10-year-old or a 10 cigarettes a day, I should say, or 50 cigarettes a day work, you get answers that are reasonable results. I have a patient and I asked him, how many cigarettes do you smoke a week? And he says, I'm a chain smoker. I'm smoking 200 a week, right? Almost 2 packs of 20 a day, right? You might even know people who are really horrible chain smokers, right? According to this model then, do you see the answer is stupid? Negative 25 means they died 25 years before they were born, right? That is stupid, right? The problem that we've got here is called extrapolation. I mentioned that before. When you use your model beyond the data, in fact, in this question here, didn't the data stop around about 20 cigarettes a week? If you start using it for people way over here can you see that the model is not even guaranteed to be accurate anymore? Now, as long as you pick numbers from 0 to 20, the range of the data, which technically would be that one, shouldn't you be reasonably confident that you're going to get an answer that's pretty decent based on your data, right? It's in your data, it's one of your numbers, you know, it's right in the middle, it should be fine. When I did the 30 cigarettes, I was pushing it a little bit. Wasn't I kind of taking the data up here? But it's close enough to 20 to probably be okay, like most of the time, but not all the time. Would you agree by the time you get to 200, don't pay any attention to the model, right? Extrapolation just means using values of X that are beyond the range of the data. So don't use it. Don't use it to predict things. Don't use it to tell me something's true. Use it inside the range to tell me it's true, and I'll believe you. Use it outside range. There's no guarantee that whatever you say is correct. Now, could it be correct? Yeah, I guess it could be. But there's no way of proving it. You haven't got data to show me. And yeah, okay, straight lines go on forever. No, they don't. Don't straight lines go on forever and then you suddenly become 18 and your height doesn't go any bigger, right? Things change sometimes. Sometimes things do keep going. But do not do it. Don't do extrapolation is basically the moral of that story. Oh, while we've got these guys here, let's talk again about a topic that we use a lot. Correlation does not mean causation, but in some circumstances, couldn't you argue that in some situations, it seems reasonable that the thing you're measuring is the main contributor to what's going on? So let's take this one. The area of a house against the value. Would you agree that there's probably not a lurking variable there? I would suggest that the area of a house is the major factor for the value, not the only one, but the major factor. Agreed? Would that seem reasonable? And would you agree that if we were doing the how long do you live question, based on the number of cigarettes, is cigarette smoking the only factor? No. There are lots of other reasons why people don't live so long. Is it their genetics? Is it their, well, people who smoke a lot, don't they also probably not exercise a lot and do other things and they don't live so long for that? But I would say that the major factor was correct. So in these two, I don't think I would argue that there was something else that was a lurking variable. Right. So how can we be aware of when we might have to be more careful? Well, sometimes it's kind of obvious. Remember the size of the children's feet and their reading age, or the number of cars that you've got and how long you live, that kind of thing. Those ones I think obviously kick in. Let's suppose that the R value for this guy is 0.8. It's not a great correlation coefficient, right? But it's okay, it's pretty good. Now, we talked about R squared, which is 0.64, which we almost always call a percentage, and that is 64%. Now, that number is quite interesting because you can interpret it in a number of ways. The formal way of interpreting it is that 64% of the variation is accounted for. In other words, 64% of the price of the house is to do with the area. Now, the opposite of that is 36% of the variation is unaccounted for. So if I was trying to put that into layman terms, I would be saying something like, the price of your house, 64% of it is because of how big it is. And the other 36% is for other things. Couldn't those other things be, I got a swimming pool, I got a view of the sea, My house is in pretty good condition. My house is in a horrible condition. My house is next to a drug den, right? 34% is unaccounted for. That allows a lot of wiggle room, doesn't it, in what your house is going to be worth. If we pretend we did this one and the R value was 0.95, then the coefficient of determination, which is the fancy name for that guy, is 0.95 squared, which is 90.25% when you turn it into percentage. Let's just call it 90. Is it 90% of the reason that you live so long, if you are a cigarette smoker, is because of the number of cigarettes you smoke? Now, what's the other 10%? Isn't the other 10% genetics and other things that you could come up with, right? Other variables that may be different from one person to the next. Does that make sense that this R squared is a way of giving you an idea of how good the fit is and gives you a kind of percentage on it, right? That's one way you can look at it. Have you ever heard people say things like, for every 10 cigarettes you smoke, you will take six years off your life? You ever heard those kind of things?
Yeah.
Right, if you want to know where it come from, it comes from this guy here. Remember that negative 0.6? Right, if you do 10 of them, isn't that negative 6? So for every 10 cigarettes you smoke, you will take 6 years off your life. Or for every 1 cigarette you smoke, you will lose about half a year of your life, you know, if you want to do it as a 1 for X. Have you noticed then that the slope is where they get that line from? So if someone then says to you, for every 10 pounds overweight you are, you'll take a year off your life expectancy, making this up, right? For every 10 pounds overweight you are, you will take 1 year off your life expectancy. Haven't they basically told me that number's -1, the slope? So that's where it comes from. Now, if I had a model, which I'm not going to draw the line off, but imagine I had a model and I told you that R squared was 4%. Would you use that model to do any predictions? Suppose I gave you a formula, if that helps. Would you use that model, that formula, to do any predictions on, if X is this, my predicted Y would be that? 4% R squared. Any takers? 4% R squared. Definitely don't use that model for anything. Another way of looking at R squared is the percentage of the time you're going to be close to the right answer. 4% of the time, my prediction will be reasonably close to the right answer. Doesn't that also mean 96% of the time I'll be miles out?
You could almost rely on it as an opposite.
Well, you could say the chances are it's not going to be that number. You're right. Pick any other number, but not that number, and you're more likely to be right than the number they gave you. So if someone builds a linear regression and they do all the calculations and they come up with a model, and then they start using it to predict things and say, oh, this is going to be the unemployment rate in 5 years from now, or this is going to be the value of the S&P 2 weeks from now. And you look at their model and you find out that their R is tiny, or in this case, that R squared is tiny. You should immediately say, useless. Whatever you tell me is going to happen, I'd probably be better predicting the opposite. I'm just as likely to be right as you are. In fact, couldn't I just pick a number from 1 to 20 and I'd probably just be as accurate? So, R squared are bad. If you get an R squared of 99%, Should you use it to predict? Heck yeah. In fact, want to be really good at getting really close 99% of the time. You're going to be wrong a couple of times. That happens with everybody. But aren't you going to be pretty good most of the time? Right? X will give you a good prediction on Y, and you could probably take it to the bank. R squares of 99% are really hard to get, because if you did that, wouldn't you have almost a perfect straight line? I mean, that's the only way you would get that kind of R value. And I mean, I guess there could be some situations where the science is so well understood that that could happen. Now, my next topic, I'm going to add to our list, are things called outliers. We've talked about them, but I'm going to tell you how outliers can affect linear regression. So there's my normal guy, and here's my best fitting straight line. Okay. Here it is now. Can we imagine we did this guy, and we'll stick to R value again, and we got an R value of 0.9. And then somebody came and said, oh, darn it, I missed one of the numbers. I forgot to put it in. And you said, okay, I'll put it in. And God and Himmel, it ends up being an outlier. .9 without the outlier. I'm about to add that outlier. What do you think should happen to the value of R when this outlier is included in the calculations? Will it get bigger? Will it get smaller? Will it stay the same?
I feel like it would stay the same for the most part, just because a majority of your
it's only one number. What damage could one number do? Well, if there's a couple of 100,000 numbers here, that won't make any difference. But see if there's only like 20 numbers here, that actually, it's like the Bill Gates factor. You remember you might have 19 people all about the same, and then Bill Gates with $40 billion, doesn't the average shoot up miles away? Outliers are dangerous. That particular one could kill the R value. It could make it if there's not a lot of points. That one outlier could kill that data. So if you are building a linear regression model, right, you're trying to get an equation, that outlier will destroy that. It will destroy something else that you might think less likely. But the line of best fit isn't that line anymore. That 1 point out of 20 numbers will do this to it. Think of it like a magnet. It'll bend the line a little bit towards it. So the line ends up being something like that. So what will happen is that the R value will go down, and won't the predictive ability of the line get worse? In other words, if I use the new formula for the red line, won't I be wrong 50% of the time? Right, an R value. Well, it's actually, that's 25%. So 75% of the time I'll be wrong. So that's what an outlier does when it's in that position. Does that make sense, that an outlier can make the R value a lot worse? Even if you think it's only one number, it actually does, in small data sets. Here's the second situation. Again, I'm going to do an outlier. I'm going to make it a little bit far. Still linear, right? Still looks pretty good. The R value, it might be 0.8 now, right? It's not as great as the first one, but it's still okay. And the same story. Oh, I missed a number. And the number this time is up here, and it's still an outlier. and I'm choosing this outlier in a very, very specific way. I'm picking the outlier so that it's in the same direction as the rest of the data. Do you see it's in the same straight line as most of the data is following? And it's important that I have my outlier here. Right. This one might surprise you. That one extra outlier that's in the same direction as the rest of the data will improve the R value. And it won't improve it by a little bit, it very often will improve it by a lot, especially if that outlier is way up here where my finger is. And you might think, well, how on earth does that work? It works because of the way that we calculate R. And if an outlier is in the same direction as the data, that one outlier has more influence than a typical one of these points would have. And so you could quite easily think that you've got a really good model. So let's take that to silliness. Imagine I've got a really, really vague model, right? It's very weak. The correlation coefficient is 0.12, right? Not a lot happening here, right? 0.12. If my outlier was here, the correlation coefficient could be 0.9. Moral of that story is outliers are bad. Outliers distort the truth. They make things look much better fit than they really do. Would you agree that is still a horrible model? It just happens to have an outlier that's pointing the same way as the rest of the data. And isn't that making you think that you've got a really good fit? Isn't that outlier making you think you've got a horrible model, when in fact that outlier is hurting your model because isn't the real data a really good fit? Now, when we did mean, mode, and median, wasn't one of the strategies, if you find an outlier, you remove it from your data? Does that seem a reasonable thing to do? So if you do a scatter plot and you see an outlier, throw it away, right? And do the model without the outlier, because won't it be much better for predictive purposes, and won't it also be closer to the truth of what the data is telling you? And it's okay to do that. But if you do that, shouldn't you tell people at the bottom, I've removed blah, 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 it's an outlier. Or I've removed 2 points because they're outliers. And then you can look at those 2 points and you can decide for yourself, was it reasonable to throw that one out? And I'd say definitely. Was it reasonable to throw that one out? I'd say you're right. I would have thrown it out as well. So suppose that.
Is there a level of data significance, like percentage, for what is considered an outlier? Like, for example, if 0.5% of your survey were just far and beyond everything else, would that still be okay to remove that as long as it's mentioned below? Or is there a certain point where it's like, okay, this isn't necessarily a group of outliers, but a secondary group within the chart?
Yeah, exactly. What you said is perfectly true. There isn't a standardized test or rule for what's allowed and what's not. Depends on the data. You could have that. Give you an example. Suppose I had my data and it looked, well, actually, the story I was going to tell, I don't want the line yet. Suppose I had my data and it really didn't have any shape at all to it, right? You are not allowed to do the following. Hey guys, My theory says that the data should be a straight line going that way. And I don't like my R value. So all these guys here and all these guys here, they're all outliers. And so I'm only going to keep the data that fits the model that I want to be true. Would you agree that is total cheating, lying, shouldn't do it?
It seems like something someone would do, though.
It is and has been done. But the rule is you must tell me who your outliers are. Now, if you tell me who your outliers, can't I reanalyze the data and say, wait a minute, why are you doing that? Because couldn't you equally decide that your model says the line goes that way, in which case, wouldn't you destroy all these numbers? Right? In other words, you throw things out that do not fit what you want to be true. That is definitely bad news, shouldn't do it, but there is a temptation. But it is possible that this happens. Can you imagine I collected data and it looked like that scatter plot? Now, if I put it into the software, the line that I would get would probably be something like that, which is a horrible fit for almost everybody, agreed?
Yeah.
But what you're really seeing here, like you were saying, isn't it really two distinct sets of data? And shouldn't you really analyze it as one set of data and then a different set of data and do each one of them with their own unique line? Would that make more sense? So, yeah, let's suppose we're collecting data on, I don't know, ages of people and potassium level, right? And the data looks like that. Do you know what I might be looking at? Couldn't I be looking at a male-female split? And that male's potassium level as they get older is different than female potassium levels as they get older. And in that case, wouldn't it be reasonable to look at this data and say, okay, what is going on here? Oh, hopefully you collected data like they were a male or a female as well, right? And I don't know, their weight or something else. And you say, males and females need to be treated separately. So that's how I would tackle that situation. I think that's one of the things you were getting at. So no, you're not allowed to throw things out because you want them to be gone because they don't agree with your expected model, what you wanted to be true. There is some, what's it called? The hockey stick. Yeah. Look it up. There was a British scientist who collected data and it's called the hockey stick. And look into it. They were very, very naughty. And they did something along the lines of what Brandon was talking about, which is being selective about who you ignore. Now, if you really want to cheat, don't tell me the outliers. So imagine I collected data and the data looked like this. If I was unscrupulous, wouldn't I forget that side of the data and only show that guy? Do you see a hockey stick? That's what the bugger's done. I don't like that data. It's not linear. It's not agreeing with what I want to be true. So I pretend that that data was never collected. That's cheating. But we are now aware of that, aren't we? So when you look at a scatter plot and a linear regression, aren't you going to look at the R value? Aren't you now going to look at what were the outliers and were they reasonable to be called an outlier? Aren't we also going to say, yes, there's a connection, but maybe it's a lurking variable. Maybe it's not X causing Y. Maybe it's something else like your age. Aidan, what's your question?
Couldn't you also do a curvilinear regression?
You should, if you wanted to be accurate, shouldn't you? See that hockey? Shouldn't you do a model that's curved? Now, software will do that. See if you give a computer software the data, right? The X and Y's of all your data points. You can then say to that computer, I want a linear. Well, if you say you want a linear, it'll try the best straight line. You could ask for a logarithmic, which will try and fit a log curve through it. You can ask for a quadratic, it'll try and stick a quadratic through it. I mean, you could do an exponential model, which basically tries to make, you know, an exponential curve through it, and it will get the best fitting whatever curve you ask it to fit it with. And that would be the honest way to do a hockey stick shape, would you? That's how you should have done it. I think that was quite good. I did a joke, then we'll actually have time to start the homework point just to show you. Once I figure out what button I'm trying to press here. Getting tired. Have you all noticed that as every week goes by, your brain gets a little bit foggier because we're getting a little bit tired?
Definitely.
Me too. I feel your pain. We're running on vapors right now. A lot of us are, at least. Okay, so are you looking at chapter 9 linear regression? Is that what you see on your screen?
Yes.
Yeah, good. Okay. So there are 12 questions. So here we go. The least squares line. So basically, there's the formula, right? The predicted y is 5 take away 7x. And it says to you, what's the value of the slope? So the answer is nothing too clever, -7. Right? If they'd asked you, what is the y-intercept, wouldn't you put in 5? Right? Now, when x changes by 1 unit, how much does the predicted y change? Well, since the slope is -7, shouldn't that mean that it reduces or decreases by 7? So when x increases by 1, the predicted y decreases by 7, and boom, there's your answer. Does that seem reasonable?
Yep.
That's how they're going to ask you those kind of questions I kind of did my own way earlier today. Question 2 is pretty much the same question, so we'll just get by that. Now, this is going to be our last question for today. I want to just show you how to start with SALT, and then that might give you a chance to do some extra homework ahead of schedule so you've got more time next week. An economist is studying the job market in the Denver area. X represents the total number of jobs in a given neighborhood. So this particular neighborhood here had 50 jobs. And Y represents the number of entry-level jobs in that neighborhood. Entry-level jobs are kind of like the bottom run of the job, right? It could be, you know, I don't know what the worst job in McDonald's is, right? It could be that job, right? It could be the person in the warehouse that just loads things into the truck, right? And then later on you become a manager, supervisor. So that's entry level. And here is a number of jobs, and here is entry level. And it asks us here, as we've done before, to do a scatter diagram of that data. And don't worry about this stuff here, I'll tell you about that in a minute. So I'm going to hit use SALT. And you should be watching SALT for a second. There we go. I want to see a scatter plot. Can anybody remember which one of these guys?
Charts and graphs.
Charts and graphs, scatter plot.
Agreed. And then hit scatter plot. And X is going to be this fella, and Y is going to be that fella. And then almost always, I have to shrink the thing back. Obviously not that much. And if you want to see the regression line, it looks like that, right? So you could look at that picture, and then when you go and look at the question, wouldn't there be 4 pictures and one of them looks like that one? I've not found that particularly easy to do, but since I've got this guy in front of me, it looks to me.
A?
I think it's that one, yeah. The scale's a little bit different, yeah. I'm pretty sure it's that one. Now, let me return to this stuff up the top here. It says complete parts A through A, given that this is true. Now, all of these numbers here are going to be used to go here, 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 and here, which is a pointless exercise because don't you just write down the numbers that you saw 2 seconds ago? Right. What you do want, however, to use is this fella, hit regression line. Select this guy, select that guy. And I'll even put the regression line in. So there we go. Now, there are lots of guys in here, most of which you won't worry about. This fella here is the correlation coefficient. So that's the R guy. So roughly it's about 0.8499. If they ask you for R squared, that is not the number. You will do 72.23% because R squared tends to be as a percentage. It's the same answer. Now, do you see this guy here? And then this guy here. These two represent the y-intercept, and this guy, the slope. So I'm going to write that down, that y hat is 0.156. Right, that guy there is the slope. And then it's going to be minus 0.5852. Now let me return to the thing.
What button did you press to get that information?
I'll go back and show it in a second. Right, that was that's the slope, and that's the intercept. Right, really it should be called the y-intercept, but they just call it the intercept. So those are 2 numbers that you would want to get. Right now, let me return back and show you what buttons I pressed, Liana, to get there. Right. So
Thank you.
okay. So here is the data. Hit use salt. Pick regression line. X is the total, Y is the total. Put in regression line, and you might want to shrink it a little bit if you want to see the line. And here are all the numbers and lots of other numbers you'll never need to look at. But the 2 that I used were, there is the y-intercept and there's the slope. So 0.156x minus that number. And if you look up here, it's not very clean, but isn't that basically the formula with a whole load of words kind of interspersed in it?
So for this result, we use more of the regression than the charts and graphs and the scatter plot.
Yeah, because this one tells you the equation of the line. Now, some of the data that you want will come from descriptive statistics, right? So if you go over to the descriptive statistics, if you hit the sum of squares, and that, you should also get, oh, do I have to redo it? I may have to redo it. There we go. I hope it, no, it resets it. Okay. Hit the sum. Right, there we are. The sum, right? Sum of squares. That guy and that guy. Let me show you what those guys are, because their name isn't as clear as what they ask you for. When they do sum of x or sum of y, that means the sum of x, and that one means the sum of y. So in my case, they just call it sum. That's what it's called in the table. And so this guy is 202, and this guy here is 28. Now they also have sum of squares, which they're going to call that guy and that guy. And when you look at that, it's called the sum of squares, which is actually a better name. And I'm looking at the data here, and this number here is 7790, and this here is 164. So these numbers that I got them from descriptive statistics. Now, if you wanted to know what the mean is, wouldn't you just divide that by whatever it was, 10 numbers, and divide that by 10 if you wanted to know X bar and Y bar? Almost all those questions that I talked about there, you're being asked to verify them, which really is a pointless exercise. Aren't those all the numbers I just mentioned? So can't you just take my word for it and rewrite them in here, right? We're not going to ask you directly to do those numbers. I'm not even sure why they wanted. Now, if you wanted to do X bar and Y bar, you would have to do a little bit of work. There's only 1, 2, 3, 4, 5, 6 pairs. If I wanted to get X bar, wouldn't I take the total and divide it by 6? And if I wanted to get Y bar, wouldn't I take the total and divide it by 6? So those two guys would be 202 and 28. So 202 divided by the 6 numbers that had X's in them. I think the other one was 22 divided by 6. That's the only two that I would actually do any kind of calculation for. Now, you know, this guy here was, what was it? Negative 0.5852. And then you notice a little X, so they wrote it kind of back to front, 0.156. So notice that, because it's almost, you wouldn't even pay attention. See the X, slope goes here. So they put the y-intercept first and then the slope second, which to me sounds backwards. So you do 2x plus 1, not 1 plus 2x, but if they want to write it that way, they do. There's a picture. R squared, I don't know what R squared is, I've forgotten, but let's pretend it's 0.45. Well, actually, technically it is 0.45, but 45% explained and 55% unexplained. And then if you wanted to get the last question, 39, wouldn't you take the equation, wherever that damn equation is, this equation, and wouldn't you replace X by 39? So you would do this negative number plus nothing 0.156 times 39, and let's pretend the answer's 12. I know I kind of zoomed through that a bit, but do you get the gist of how you're going to use it? How pretty much all the number crunching is going to be coming through using the sort button. The R value you'll get in sort, the R squared value you'll get in sort, the y-intercept is in sort, the coefficient of X, which I believe is what they call that guy, is in sort. That's the only one I had to do a little calculation. And I took the number that was this guy and divided it by 6. And I took this number and I divided it by 6. So that's the only one that I would do a calculation for. All these other numbers here, here, and eventually here, we would get them just by looking it up the right place for salt. Now that I've done that, I'm a little bit curious to find out what the R value was. So if we go here, oh, 0.8499 is the R value. R squared is what, 0.7223. Doesn't that count as 72.23%? So roughly about 72% of the time you're going to get a pretty decent answer using the model. But doesn't that also mean that there's another 28% unaccounted for other reasons? And you don't need this, but I'm going to put a low confidence bar in it. You see that little funny shape? Which might answer Brandon's question. How far away do you need to be an outlier, right? See these little dotted lines? See them here? Here? That's how far away you need to be an outlier, at least on the outsides. That's here and here. So if I had a dot where my pointer is, it'd be okay. If it was down here, it'd be an outlier. And we don't use that. But if you wanted to see it, that's what it would be. Okay, guys. Last name. Bye-bye. Have some good jokes that are suitable for Monday. Liana, you got a 4-year-old. They should be full of good, really corny jokes.
Listen, I'll be
Right.
ready, I promise.
Gotcha. Zach, you're not going to tell me any more jokes about horses. I think it was you that did the horse joke, or Brandon.
Oh, no, I was
Oh, it was Brandon. Brandon's claiming the horse joke.
in the
Zach,
carpet
you
kitchen.
and the
did the
carpet one. You did the other one, right? So better material for next week, right, guys? Okay, bye-bye. I'll hang about for any questions.
Where did you say you posted that video at? I was looking for it. I didn't.
Oh, okay. I'm going to show you right now. Hold on a second. I'll load it up so you can find it. And I have no idea where I am right now. Leave student view. Come on. There we go. Almost ready to show you where it is. Okay, I'll go back into student view so it looks more like you would see. So here goes. Oh, you've been seeing it all the time. Okay. When you go into Canvas, it might look like this. The one that says welcome, choose that tab. Go down to this one here that has the Zoom lectures. It was week 6 that we're on. And there it is there.
All right, perfect. Thank you.
Okay. Yeah, Lana, you got a question for me?
Nope,
Or
I
you
was
just-
watching to see it was on the same spot. So
Is that what you needed to see?
yeah. Thank you.
Did
I'll
you-
see
did-
you on Monday.
Did you like my joke?
I did.
Are you going to tell your husband
I might.
it? Okay,
Probably
bye-bye
pay
for now.
attention. Thank you. Bye.
Bye-bye.